Continuing to continue 9.5, hazardous weather and geographic regions at risk. Another type of hazardous weather are mountain windstorms. They develop seasonally on the downwind side of mountain ranges or glacial ice fields. Mountains block prevailing winds and can, under specific conditions, cause winds to move quickly down slopes. Examples include the Chinooks east of the Rocky Mountains and the Santa Ana winds in Southern California. The image shows smoke from wildfires being blown away from the coast by the Santa Ana winds. These mountain windstorms can cause roof and tree damage, blow cars off highways, and contribute to large wildfires. The mechanism is shown in this cartoon, specifically for Chinook winds, but is very similar to other mountain windstorms. Cool, moist air is forced over a mountain. As it rises, it loses moisture through condensation and precipitation, which also heats the air through the latent heat of condensation. But it is still pretty cold as it reaches the top of the mountain. As it goes down the other side of the mountain, the air begins to warm, but this warm air is dry. Remember, it rained out on the other side of the mountain. So this warm air needs moisture, and picks it up from the streams, snow, plants, anything it can, drying out the other side of the mountain. It makes conditions pretty good for wildfires. Another type of hazardous weather, dust storms. These are strong windstorms in which dust reduces visibility for a significant amount of time. It can exceed 30 miles per hour with visibility less than 0.5 miles. It can be several hundreds kilometers in diameter and carry 100 million tons of dust. It is a safety hazard for travel and can affect climate and human health. The smallest particles, less than 0.01 millimeters in diameter, travel long distances in upper atmosphere, like over oceans. The 1930s Dust Bowl is a classic example of a particularly damaging series of dust storms. The image on the left is from May 21st, 1937 in Kansas, as topsoil is blown away. The image on the right is an impressive dust storm from southern Arizona that caused a huge pileup on the freeway. In contrast, sandstorms are desert phenomena where sand transported in a cloud that rarely extends above 2 meters or 6.5 feet above land. They generally have larger particles that are being blown around, sand-sized, in fact. Along with dust storms, sandstorms occur mostly in mid-latitude, semi-arid, and arid regions. Hopefully that makes sense. The images are of two sandstorms, one in Egypt by the pyramids. Heat waves are also under the topic of hazardous weather. They are prolonged periods of extreme heat that are both longer and hotter than normal. In the U.S., about 2,000 people were killed by heat waves from 1992 through 2002. Heat waves are associated with long areas of high pressure called ridges. The cartoon shows how a high pressure system with a high pressure ridge aloft can create a cap that traps air in one place as it warms. Remember that the air warms as long-wave electromagnetic radiation emanates from the surface of the Earth. This static air is constantly being warmed, can lead to a heat wave. Due to prevailing winds, wet conditions generally form on the west of the ridge, and dry conditions to the east of the ridge. So heat waves can accompany either severe humidity or extreme dryness. Personally, I'd rather experience the dry heat side, which is probably due to the heat index, which is the body's perception of air temperature. So here is a heat index chart. Across the top, we have relative humidity, and along the side, we have air temperature. The numbers that fill in most of the chart are the body's perception of temperature. Take a moment to look at the numbers. Do you see any trends? A trend that I notice is that at any given temperature, as relative humidity increases, the body's perceived temperature also increases. For example, at 94 degrees Fahrenheit and 40% relative humidity, my body would feel like it was actually 97 degrees Fahrenheit. But at 85% relative humidity, my body would feel like it was 135 degrees Fahrenheit. Notice the color coding too. Dark orange for extreme danger, through to light yellow for caution. So what do you do to avoid heat stroke when it's 94 and humid? This next slide lists some helpful, hopefully common sense safety tips. Take a moment to look at the table of personal adjustment for heat waves. This table is also found in your book. So, would a greasy burger barbecue with beer in the sun while wearing a tight black t-shirt and long jeans be a smart or dumb idea when it's hot and humid? Hopefully you already know that would be a dumb idea, but it happens sometimes. So what do you do if someone's at the barbecue, starts acting funny, maybe disoriented or complains of cramps or isn't sweating or has a huge headache? Do you ignore it because they just can't handle a party? Hopefully not, because you are aware that the individual is exhibiting signs of heat exhaustion and heat stroke could be imminent. What do you do? Hopefully you get them in the shade ASAP, or into air conditioning, or get ice packs on their skin. You may even need to call 911. Okay, so remember, when it's hot, 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 don't hang out or exercise for a long time in the sun. Use air conditioning and cold showers. Use fans to blow hot air away from you. Stay hydrated, eat your veggies and fruits, wear loose-fitting and light-colored clothes, and don't leave things in closed vehicles. Like I said before, hopefully this just is all super common sense, but heat stroke still happens. Let's just make sure it doesn't happen to us or anyone we know. 9.6. Human interaction with weather. We can certainly make some severe weather worse. For instance, land use, such as agriculture and overgrazing, can contribute to dust storms. The picture here is of one stunning dust storm rolling across an arid landscape. Everyone, better get inside. Another effect of land use in cities and suburbs causes the urban heat island effect. An urban area can be 12 degrees Celsius or 22 degrees Fahrenheit warmer than the countryside. That's quite a bit warmer. The picture is a heat image of Boston, Massachusetts surface temperatures in 2009. There is no scale, but the red and yellow colors indicate warmer temperatures than the blue and greens. This is a graph entitled the Urban Heat Island Profile, with temperature in Celsius and Fahrenheit on the y-axis and different land uses along the x-axis. Apparently, this is a typical late summer afternoon profile. Take a moment to look at the graph. Where is it the hottest? Where is it the coolest? Are parks as cool as a rural countryside? Does housing spacing seem to affect the heat island effect? So what causes the urban heat island effect? What do you think is causing the urban island heat effect? The answer is mostly all that asphalt and concrete. Get hotter and retain heat longer than vegetation and even bare soil. There is even some evidence that the urban heat island effect is affecting local weather conditions. What do you think the effects of a constant local low-pressure area could be on the local weather? Global warming is another example of human interaction with weather. As further discussed in the climate change section, global warming increases heat index and heat waves, increases intensity of precipitation, increases risk of drought, and increases intensities of hurricanes, typhoons, and other tropical cyclones. Both graphs have time along the x-axis and temperature anomaly in degrees Celsius along the y-axis. And yes, these graphs are also in the climate change section. The top graph shows that though there is significant variation in temperature, the general trend is up. Up in temperature. The bottom graph shows temperature predictions from several different climate models, and by 2100, the temperature is expected to be even warmer than the present. A seemingly small temperature increase gives our atmosphere and the weather systems a whole heap more energy, making the severe weather hazard more common and more hazardous. The future looks exciting, and hopefully we'll be prepared enough so that it won't be too costly. 9.7. Linkages with other hazards. Severe weather can cause a bunch of other hazards such as flooding, mass wasting, wildfires, and tropical and extratropical cyclones. Can you think of more? There are more. The pictures of a flood are of a flood and a cyclone. Global climate change can exacerbate the severe weather hazard as we discussed in the climate change chapter. What do you think? Are earthquakes, volcanoes, or meteorite impacts linked to the severe weather hazard? No. If you'd like to share other links between the severe weather hazard and other natural hazards, please email me. 9.8. Natural service functions of severe weather. There are many, but here are a few. Severe weather contributes to the health of forests. Wildfires clear old growth. Windstorms topple dead trees, and that creates and maintains plant and animal habitats. Severe weather is also a source of water. Yay for hydrology! There are also an aesthetic value to severe weather. It can be beautiful, especially if you are not out in it. The clouds, snow, lightning, etc. can be stunning. Severe weather can also stimulate tourism, as in tornado chasing. The picture to the right is a fantastic example of a tornado, and I am not sure who is doing the chasing, the photographer or the tornado. 9.9. Minimizing severe weather hazards. This generally involves a lot of forecasting and prediction. Though it is difficult to accurately forecast weather events all the time, Doppler radar is good at detecting clouds, rain, ice particles, etc. In particular, pulse Doppler radar is used. The Doppler effect is used to calculate the location and velocity of these weather systems, which greatly aid in severe weather forecasting and prediction, especially short-term hours prediction. In severe weather, a watch is the possibility of severe weather developing, i.e. conditions are favorable for severe weather to occur. In contrast, a warning means severe weather has been spotted. Take action. As you may have noticed, forecasting and prediction of severe weather is not always entirely accurate. Things that are particularly difficult to predict are tornado intensity and amounts of snow and ice. Nowcasting makes real-time, i.e. within the next 6 hours, predictions of the intensity of some severe weather events. It uses radar, satellites, and weather station data once storms have formed, essentially to tell people if they are in immediate danger. And we will continue with adjustment to the hazard in just a little bit.